All right, so let's go ahead and move on with our next example. That is going to be 10.7. Consider the father pushing a playground merry-go-round in this figure. He exerts a force of 250 newtons. So our force is 250 newtons at the edge of a 50 kilogram merry-go-round, which has a radius r of 1.5 meters. And we want to calculate the angular acceleration produced in both of these cases. So our first case is going to be when no one is on the merry-go-round. Okay, so there's no additional mass or anything like that. Okay, so we just learned that our net torque is equal to inertia times alpha, or our velocity, our rotational or angular velocity, acceleration. I'm sorry, rotational acceleration. Okay, so we have net torque equals our inertia times our angular acceleration. Okay, so we can use this information and a couple of other equations to find our alpha. Okay, so let's go ahead and solve for it here. We have net torque over our inertia. Okay, so here, remember that torque equals our radius times our force, okay, times the angle between these two, which in this case is 90. So this is just going to be 1 for our sine theta. So we can go ahead and plug that in, r times f, okay, times 1, since again our theta is 90 degrees. Okay, it's perpendicular. And our inertia around a circle, okay, is going to be 1/2 times our mass times our radius squared. Okay, so we can go ahead and plug these values in. Okay, and so we have our radius is 1.5 meters. Our force is 250 newtons, okay, divided by 1/2. Our mass is 50 kilograms, and our radius again is 1.5 meters squared, okay. So if we plug that into a calculator, we get 1.5 times 250, which is 375, and this is going to be in Newton meters, which makes sense. That's what our torque units are. And then we have 1/2 times 50 times 1.5 squared, which is 56.25. And this is going to be kilograms meters squared. Okay. So now we can take our 375 divided by the value on the bottom, and we get 6.67. Okay. And our units here, remember that newtons is kilogram meters per second squared. Okay, that's our Newton times our meter divided by kilogram meters squared. Okay, so as you notice, our kilograms cancel, all of our meters cancel, and so we're left with just over seconds squared, okay, which just means radians per second squared. Remember that we kind of have to just insert those radians here. Okay, so this is my angular acceleration in this first case. Okay, All right, so the second case is going to be when we do have a child on it. It is a child with 18 kilograms of mass and sitting 1.25 meters away from the center. Okay, so let's kind of cross that. Okay, so the only thing that's going to change here, as you notice, our torque is going to be the same because our force is the same, and so is our radius where that torque is being applied, or that force is being applied, but our inertia is going to be different. Okay, so this is our first inertia, but we need a total inertia of the entire system. So that's going to be the first inertia that we just found, and this inertia of the kid, we'll call that I2. Okay, so let's go ahead and calculate that. So our first one, we knew came out to 56.25 kilogram meters squared. And so now we want to add our second inertia, 1/2 times our mass, which is 18 kilograms, and our radius at which that inertia is, so that's going to be 1.25 meters squared. Okay, so let's go ahead and do that. 0.5 times 18 times 1.25 squared. That gives me 14.1. Okay, so let's add that to 56.25 and we get 70.3 kilograms meters squared. Okay, so this is my total inertia. And now let me go ahead and plug this other stuff in. So we have our alpha equals our net torque over our inertia. That is going to be this, again, it's going to be the same on top, so it's going to be 375 Newton meters divided by 70.3 kilogram meters squared, 375, and that is going to give me 5.33 radians per second squared. Okay, so notice the difference here. Okay, these values are different. Okay, the first one, there's a higher acceleration than the second one, and that makes sense because there is more inertia on the second one. Okay, all right. Oops. So that is example 10.7. Let me go back to our PowerPoint now. All right, so we just learned about our inertia, and now let's go ahead and start looking at energy. Okay, so kinetic energy. We want to look at rotational kinetic energy in particular. Okay, so before we were able to talk about kinetic energy in one dimension and in two dimensions, now we want to be able to describe its kinetic energy of some kind of rotational motion. Okay, so what we'll do is we'll start with a force that's parallel to the displacement. Okay, and that is like in this figure. So we've got some force parallel to its displacement. Okay, it's parallel to delta S. Let me get a pen. Okay. Now, for that situation, we can say that our net work is going to equal our net force times our delta S. Okay, so our displacement. Okay. Then we can also say, let's go ahead and multiply and divide by R. Okay. The reason we can just do that, kind of like we did earlier, is because R over R is just equal to 1. Okay, so we're able to manipulate equations like this. Okay. Now we can call that F times R is torque. Okay, so we saw that previously. And that delta S over R is theta. Okay, so again, torque is RF, okay? And remember that our displacement, delta S, was the same as R times theta, and so that's what we're plugging in here, okay? Now we call this rotational work. Okay, so our net work equals to net torque times theta is our rotational work. Okay, so if we want to obtain rotational kinetic energy, okay, we need to note this here, that this is the same thing as saying our rotational work is going to also be equal to I times alpha theta. Remember that torque, net torque, that we looked at before is equal to our inertia times our acceleration, our angular acceleration. Okay, so we note this. Then we take this equation. Okay, so this is one of our kinetic equations for motion, and that's in rotational. Okay. And we manipulate it such that we solve for A times theta, alpha times theta, okay? And we can go ahead and plug that into our work, and we obtain this theorem. It's called the work energy theorem for rotational motion, okay? And, you can notice that when we plug this in, we obtain this, and these terms look very similar to our kinetic energy in one dimension. So remember, our kinetic energy is equal to 1/2 mass times velocity squared. Okay, this is exactly what this is saying for rotation. Okay, so we go ahead and can say that our rotational kinetic energy is equal to 1/2 times our inertia times our omega squared, which is again our angular velocity. Okay, so I know that this was a lot of kind of theory behind how we get there, but just understand kind of where it comes from and how to use these equations, obviously. So I'm going to go through and do some more examples with this, but again, just wanting you to understand these different terms and such. So we have our rotational work, we have our work energy theorem, and we have our rotational kinetic energy here. Okay. So we're going to go ahead in the next video, since I'm running out of time, go through some examples of this rotational kinetic energy.